If you go to Sakai to lecture materials to the subfolder that says skin, bone, and muscles, you're going to see a link to something called Scaling Laws and the B movie monsters. And if you click on it, you're going to see an article by Michael LaBarbera. Uh, what do you need to know about this? Well, that might be part of a bonus question, for instance, at the next exam. So I'll just go over it very briefly. And that is um, about scaling laws. Now, if you have read the very first handout that I gave you about Introduction to Anatomy and Physiology, I say there that there are no laws in biology. There are generalizations and principles and rules and all sorts of things, but there's no law because there's nothing that you can put into formula, mathematical formula, and that will apply to every situation in every organism. There are always exceptions. The closest to what we have as a law in biology is the scaling law, and that is a principle from physics or basic mathematics that uh, size matters, that things don't change at the same rate. If you have any kind of a body, a cube, a sphere, or a human body, and you change the size, what you're changing are linear dimensions. So if you keep the same shape, the linear dimensions are going to be different. Now, this article is talking, using a lot of different animals as examples. I would like to, for you to focus on the first two examples, the incredible shrinking man, where a human is reduced to the size of about an inch, and the King Kong, which is a gorilla, which is kind of human shape, increased to great size. Those are linear measures. So we're not, in this course concerned much with, whales and elephants and pygmy shrews and things like that. We are concerned with humans, but there's a big difference in size between humans. So you're going to be in some kind of a medical field, and sometimes your patient is a newborn or a toddler, and sometimes it's Shaquille O'Neal. They are going to have different problems. They're going to have a lot of things different because of the differences in their size, although their shape is the same. So let's say that Shaquille O'Neal is four times taller than the toddler. Four times taller than the toddler, which means the length of everything is four times longer. His femur is four times longer. His humerus is four times longer. His face is four times longer. Everything is four times longer because he's four times taller. But you can't extrapolate from that and say, well, it's just okay that the baby or toddler and the Shaquille O'Neal are going to have the same uh, medical issues or that their physiology is going to work the same. Because whenever you change linear dimensions of an object, the surface areas change by a square of it. So the surface of the skin, the cross section of a bone, the surface of the respiratory epithelium in the alveoli in the lungs, the surface of the intestine on the inside. All of that is not going to be just four times more. It's going to be four times four more. That is 16 times more. There's going to be 16 times more surface, although there's only a four times difference in length. And surfaces are important. Volumes are also important. And the volume is not going to increase four times. It's not going to increase 16 times. It's going to increase four cubed. Four times four times four. That's what, 64? That is a big difference. And why is it important? Because volume is an important measure of some things, and surface is an important measure of some other things. And physiology relies on the surface to volume ratios. So, for instance, if you are 4 times as big, that means you're going to have 64 times greater mass, greater volume. So, let's say greater mass. You're going to have 64 times more muscle mass and liver mass, and all of those volumes are going to be 64 times more, which means that all of those cells in your body are going to produce 64 times more heat as they break down glucose and make errors. That heat is going to overheat you, right? So it needs to be released. How is it released? Via skin, right? Mostly via skin. Sweating helps. A little bit might be through breath. Um but the surface of your skin is not 64 times greater, it's only 16 times greater, which means that Shaquille O'Neal is going to have a much, much greater chance of overheating than a toddler because his surface to volume ratio is very, very different. His surface is relatively small compared to his volume. So his ability to radiate heat into the environment is much, much smaller than ability of his body to produce that heat. On the other hand, the toddler has a different surface to volume ratio, so it's much more likely to freeze than to overheat. And of course, if you look at animals, tiny little shrews are going to freeze and constantly have to eat in order to be able to produce all that heat, while enormous animals are going to have trouble cooling off. That's one of the reasons why people think that dinosaurs were warm blooded. Well, they got warm blooded as they were growing up, and then at the end, they were so enormous they could not lose heat over their surface of the skin. It's not enough. So they have this furnace on the inside, enormous volume that is constantly producing some heat, but they no ability to lose it. So they stayed warm blooded for the rest of their lives without having to have a huge metabolism. Um, so it is, an example where a surface to volume ratio is important. I work with horses and teach horseback riding lessons. A lot of people have this idea that horses are going to get cold if it snows or rains on. Horses love Siberia and Canada, and then you barely find them in Africa, and it's really difficult for them down in Florida because they're large animals, which means they have a small surface to volume ratio, have relatively small surface to emit heat, and relatively large volume to produce heat. So they don't really need all those blankets that we put on them in climes like this. On the other hand, we have to worry about them overheating when it's summer in North Carolina and giving cold baths and things like that. Shade, fans in their stalls. Um, so that's one thing that's going to be different between a small person and a large person. Another one is respiratory system, right? So when you have 64 times more volume, you have a need for 64 times more oxygen. And yet your surface area of your alveoli is only going to be 16 times bigger, not 64. So it's going to be more difficult for Shaquille O'Neal to feed oxygen to all of its cells than it is to a toddler. On the other hand, when you do shrink somebody like an incredible shrinking man, his problem is that his surface is getting smaller at a much slower pace than his volume. So no problem breathing, getting enough oxygen for all the cells in the body. The problem for incredible shrinking man is that the alveoli are going to collapse because of the surface tension and the surfactant, a protein that our alveoli secrete in order to counteract the surface tension, uh, can work in alveoli of normal size, but if you're 1 inch tall, there is no such protein that can counteract that amount of surface tension, and those alveoli would collapse with the first exhalation of the incredible shrinking man, and he would die of asphyxiation. He would die of not being able to breathe. So you can think about the same thing with the digestive system. You need to bring in enough food for a larger body, 64 times larger body, yet the surface area of the inside of your intestine is only 16 times bigger, and you need that surface. It's the surface that determines how much food, molecules from food can be brought into the body, just like the surface of the respiratory membrane is determining how much oxygen you can bring in and how much carbon dioxide you can release. So you can think of the consequences of that. One of the consequences of all of this is the smaller bodies have higher metabolism than lower bodies, kind of allowing the larger bodies to survive with that larger volume by slowing its metabolism, lowering its metabolism. And this is something that you need to know because even within humans, babies and toddlers have much higher metabolisms than adults. Smaller humans are going to have lower metabolism than large humans. There's even a little bit of a sex difference with men having slightly higher metabolism than women. So that's all we need to know about scaling laws. An example of a law of physics that actually applies to biology and closest to having a law in biology, and thus something to keep back in mind when you're, later doing clinical work, that the volume and the mass of the person is uh, is very important, and that it's going to be different than the changes in the surface, which is different than changes in the length. So the scaling laws are something that are not in your textbook. It should be used to be in the older textbooks, but I'm not going to ask a lot of lots of nitty gritty questions about this, but I think that it's something that we can put in a bonus question for those who want to get more points and who want to study more and learn more and know more. Thank you.